So welcome everyone to KAIX Distinguished Lecture in Mathematics. It's my great pleasure to introduce Dave Gabay from Princeton University. I'll be very brief, although there are many wonderful things to talk about him to spare more time for actual math. So he's well known for his many works in low dimensional topology, including the resolution of Lefferts fiber conjecture and Snell conjecture for hyperbolic true manifold property R conjecture, and also is a pioneer in the theory of top foliation in essential laminations, which are one of my favorite objects in mathematics. He received Oscar Veblen Prize in Geometry in 2004 and the Clay Research Award in 2009, and he has been invited to many distinguished lectures. And he has been at Princeton since 2001. So let's welcome Professor Gabay for today's lecture.
Well, thank you, Harry. Thank you for the nice introduction, and thanks everybody for coming. It's my pleasure to be here to give these lectures and the opportunity to talk about some things that I find it interesting. So my first lecture is going to be on the four-dimensional light bulb theorem, and well, that's a theorem about the study of embedded two spheres in four manifolds, and more generally about sort of embeddings of two disks in four manifolds. And so, well, just as a very brief introduction, the study of spheres and other spheres, I mean, that's not theory, right? I mean, one-dimensional spheres and three spheres, that's classical knot theory, and two spheres in four manifolds, two knot theory, or two spheres in the four sphere. That's a venerable subject that goes back to Emil Artin in the 20s, where he found these spun knots, and already he was able to show, I mean, that's an amazingly rich subject, that sort of for example, every fundamental group of a classical knot is represented as the fundamental group of the complement of a two knot. So this talk is about the four-dimensional light bulb theorem. But before I go there, let me talk about what's known as the three-dimensional light bulb theorem. And the three-dimensional light bulb theorem is about knots, one-dimensional knots in S2 cross S1. So here in the top left, here's the way I'm depicting sort of S2 cross S1. The green sphere, that's sort of a horizontal S2, and you go vertically, that's the S1. And so here's a knot which has the property that it intersects this green sphere exactly once transversely. And the three-dimensional light bulb theorem says that if you have a knot in S2 cross S1 that intersects the sphere transversely exactly once, then it's in fact isotopic to the standard vertical knot. And say the statement of the four-dimensional light bulb theorem. So remember, in dimension 3, we had S2 cross S1. And here we have S2 cross S2. And so S2, this S2 cross point, that's like the green sphere. But now we have this standard vertical sphere, that's like the standard S1 and S2 cross S1. And notice this guy has the property that it intersects S2 cross point cross S2 intersects S2 cross point transversely in a single point. So the light bulb theorem, if it was exactly analogous, would say that if you had another two sphere which intersected this horizontal sphere exactly once, then it would be isotopic to the standard vertical sphere. Well, that can't be true as stated, because it's easy to construct spheres which have that property that aren't homologous. I mean, you could take sort of the vertical sphere and add some number of copies of the horizontal one, and you're changing the homology class. So, I mean, isotopy certainly preserves the homology class. So the theorem is that, subject to the condition that so if you have a sphere that intersects the horizontal sphere exactly once transversely, and it's homotopic to the vertical one, then in fact it's homotopic. It's isotopic by an isotopy fixing the horizontal sphere pointwise. And in fact, if the two spheres coincide in the neighborhood of the horizontal one, you could do the isotopy, fixing a neighborhood pointwise. And I should say that, well, this was proven, well, maybe I first talked about it around 2017. So about 30 years earlier, Rick Litherland proved that, in fact, there's a diffeomorphism of S2 cross S2, which takes the standard vertical sphere to the other one. In fact, that diffeomorphism is pseudo-isotopic to the identity, whatever that is. And coincidentally, Matsumoto proved this theorem in the topological category. So there's a topological isotopy taking sort of this funny sphere to the standard one. I should say that there's a much more general theorem that says that if you have two different two spheres, if you have just a general four manifold, and well, subject to this condition on the fundamental group has no two torsion. In other words, every non-trivial element, there's no non-trivial element of order 2, then if you have two spheres that have a common dual sphere and they're homotopic, then they're in fact isotopic, fixing the dual sphere pointwise. So the dual sphere is the word I use for like this green sphere. It's simply an embedded sphere with trivial normal bundle. And so if you have a given sphere, another sphere is considered to be a dual sphere if it's embedded, intersects transversely once, it's trivial normal bundle. So the theorem is that if you have two spheres that are homotopic with a common dual sphere, subject to this condition on fundamental group, then homotopy implies isotopy. And so soon after this theorem, Hannah Schwartz, in her PhD thesis, showed, in fact, that this two torsion condition is a necessary one. So in fact, there's a four manifold and a homotopy class with two different isotopy classes with the same dual sphere. And in fact, these spheres are not even concordant. In other words, concordance means that if you have your manifold, you can look at manifold cross the interval, and you look at one sphere manifold cross 0, not one other sphere cross I. And if you could sort of connect them by embedded sphere cross I, that means they're concordant. So in fact, these spheres aren't even concordant, although if you pass to like a twofold cover, then they suddenly become isotopic. And on S2 cross S2, you have an S2 with a trivial normal bundle, then an application of the light bulb theorem is that if you have a essential two disk, its boundaries in the boundary of S2 cross D2, then you can isotope it to the standard two disk, provided the boundary curve is unknotted in the boundary S2 cross S1. And there's actually a slightly stronger version that you can do this isotopy fixing the boundary pointwise, provided that the disk represents the right relative homology class. And so you could, so you could use this to actually understand that modulo diff of the four-ball, that is modulo diffeomorphism that's localized in a four-ball, that diff of S2 cross D2 is pi 0 is trivial. And any two diffeomorphisms of S2 cross S2, which are homotopic to identity, or isotopic to identity modulo diffeomorphisms supported in a four-ball. I mean, it's an open question whether diff 0 of a four-ball, diffeomorphisms of the four-ball, which fix the boundary pointwise, is isotopic to identity. And sort of another version of the light bulb theorem is that if you have a two disk in the four sphere, and suppose that two disk has its boundary is the standard circle. So the standard circle bounds the standard round two disk. So the light bulb theorem says that that you can, if you have two smooth disks, then there's a smooth isotopy taking one to the other, fixing the boundary pointwise. So, right. So anyway, there's some other applications which I don't have time to talk.
Let's continue on the second part of the lecture.
We'll say a ball is knotted. Say, and if the ambient space is Sn, we'll say that the ball's knotted if the boundary of the ball is like a standard n-2 sphere, and but the ball is not isotopic relative boundary to the standard n-1 ball. So I, here's like classic dimension. So if we're in n equals 2, then you can look at, here's like a random arc that I've drawn, and if you have any knot, you can just sort of isotop it relative boundary to like the standard one. In dimension 3, well, again, both these things more or less go 100 years ago. Actually, I mentioned this theorem in dimension 3 that up to isotopy fixing the boundary pointwise, then disks are unique in 3 space. More, you could use like Alexander's proof of Schoenflies theorem in dimension 3, at least in PL category. So if you go to higher dimensions, then there's this beautiful book of Hatcher Wagner on pseudoisotopy, and they prove that if for n bigger than or equal to 6, then there's knotted n-1 balls in the n sphere. So that leaves sort of 2 dimensions. The question about knotted 3 balls in the 4 sphere and knotted 4 balls in the 5 sphere. And so the talk today is about, actually, I should say what I was, my motivation for the light bulb theorem to start with, my motivation was really about knotted 3 balls in the 4 sphere. But behind all this is the Cerf-Pillay theorem, which I mentioned. Actually, I stated a very special case of it, but the Cerf-Pillay theorem is basically a theorem about that balls in connected manifolds of any dimension, codimension. Except if a ball is codimension 0, then you need their orientations to coincide. So the theorem is that if you have two K balls in a connected manifold, then there's an ambient isotopy taking one to the other. So here's our theorem, which is if you look at diff 0 of S1 cross S3 modulo diff B4 fixing the boundary, then this is infinitely generated group. And also diff of S1 cross B3 that fixes the boundary modulo diff B4, that's also infinitely generated. So using these other formulations, consequence is that there's not 3 balls in the first sphere, and there's also knotted separating S3s in S1 cross S3. I'm sorry so far over time, but as I mentioned, well, basically from 100 years ago, we understood that knotted 1 balls in 2 space and 2 balls in 3 space are standard, and there's missing 2 dimensions, 3 balls in 4 space, 4 balls in 5 space. One thing about hyperbolic geometry, an incredible factor of hyperbolic geometry is that if you have a manifold of, the loose form of Mostel rigidity is that hyperbolic metrics of manifolds of dimension 3 and higher are unique. But the thing is, what's not said is unique up to what? And Mostel's theorem says that if you have 2 metrics on a hyperbolic manifold of dimension n bigger than or equal to 3, then there's a diffeomorphism of the manifold with metric 1, well, an isometry, manifold with metric 1 to manifold with metric 2, and this isometry is homotopic to the identity. What Mostel doesn't say is that this isometry is isotopic to identity. In other words, that in the space of metrics, that to have a closed hyperbolic 3 manifold, the space of hyperbolic metrics is contractible. But on the other hand, if you go to high dimensions, Farrell and Antonada showed that in dimension 10 and higher, the space of hyperbolic metrics isn't even connected. And so anyway, we conjecture that in fact all dimensions bigger or equal to 4, the space of hyperbolic metrics is not connected. Anyway, thank you very much for the invitation, and I hope I wasn't too technical. Somewhat interesting. So.
It was absolutely beautiful. Thank you very much.